Good morning, everyone. I am Sunil Kumar Vishwakarma, Assistant Professor, Computer Science and Engineering Department, School of Engineering, Babu Banarsi Das University, Lucknow. Today, I am taking the subject computer network, and the one of the interesting topic of network layer is routing. So, first of all, I am going to tell you what is routing and how it works. So, the main function of network layer is routing. And what it routes packets from the source machine to the destination machine. So in most of the subnets means the part of the networks, packets will require multiple hops to make the journey. Okay, so the only exception is for the broadcast networks, but here routing is an issue if the source and destination are not on the same network, because it is not happen always. It is not the case always. Okay. So this routing algorithm that choose the routes and the data structures that they use are a major area of the network layer designs. So in this lecture, we are going to discuss the routing algorithms. So we can say that routing algorithm is the part of the network layer software which is responsible for deciding which output line an incoming packet should be transmitted on which output line it will transmit the packets. If the subnet uses datagrams, it may change to the next time. But if the subnet uses virtual circuits internally, routing decisions are made only when a new virtual circuit is being set up. So, therefore, data packets just follow the previously established route. Okay. So, it is sometimes useful to make a distinction between routing, which is making the decision which routes to use, and forwarding. Okay. One of the important factors, stability is also an important goal for the routing algorithms. There exist routing algorithms that never converge to equilibrium, no matter how long they run. Okay. So now we are focusing to the desired properties of a routing algorithm. These properties are the desired properties. So what a routing algorithm, which property it should have? So first property is correctness. What do you mean by correctness? The routing should be done properly and correctly so that the packets may reach their proper destination. If there will not be correctness, the packet maybe do not reach to the correct destination. So there should be correctness. Now the second point is simplicity. Simplicity means the routing should be done in a simple manner so that the overhead is as low as possible. Overhead, you can say the extra resources used will be as low as possible. With increasing the complexity of the routing algorithms, the overhead also increases. So routing algorithm must be simple. Now the third point is robustness. What is robustness? Once a major network becomes operative, it may be expected to run continuously for years without any failures. It may be the possibility. but the algorithms designed for routing should be robust enough to handle hardware and software failures, because there may be possibility of hardware failure or software failures. So our algorithm should be designed in such a way that routing should be robust. It can handle these type of failures, and it should be able to cope up with the changes in the topology and traffic, okay, without requiring all jobs in all hosts to be aborted and the network rebooted every time some router goes down. So there should be robustness, means a routing algorithm should not go down in odd situations. Okay, now the fourth point is stability. Stability means routing algorithm should be stable under all possible circumstances. Whatever the circumstance is, it should be stable. Next is fairness. What is fairness? Every node connected to the network should get a fair chance of transmitting their packets. There should not be any biasing, and that one node in the network is sending the packets and another node is not getting the chance to send the packets. Okay, so in fairness, every node should get a fair chance of transmitting their packets. So this is generally done on a first come first serve basis. So this is the fifth property, desired property of a routing algorithms. Now the last property of routing algorithm is optimality. What do you mean by optimality? The routing algorithm should be optimal in terms of throughput and minimizing packet delays. Here there is a trade-off and one has to choose depending on his suitability. What do you mean by throughput? Throughput means, if we talk about throughput in the network, so we can say the number of packets sent per second, amount of data sent per second can be throughput. Okay, so these are the properties of routing algorithms. Now next, coming to the next slide, classification of routing algorithms. So routing algorithms are classified into two categories. First one is adaptive and another one is non-adaptive algorithms. Okay, what is non-adaptive algorithms? Non-adaptive algorithms do not base their routing decisions on measurement or estimates of the current traffic and topology. Okay, or we can say that adaptive algorithms are dynamic routing algorithms, and non-adaptive routing algorithms are static routing algorithms. What do you mean by static and dynamic routing algorithms? Adaptive means the routing decisions depends on the current traffic and the current topology. In adaptive algorithms, routing decisions are taken online, but in non-adaptive algorithms, routing decision is taken in advance, or we can say statically, offline. And non-adaptive algorithms do not take in consideration the current traffic and the current topology. Okay, so this is the basic difference between adaptive and non-adaptive algorithms. Now, routing algorithms. There are so many routing algorithms are listed here. The first one is the optimality principle. The second one is the shortest path routing. Third is flooding. Then distance vector routing, link stat routing, hierarchical routing, broadcast routing, multicast routing, routing for mobile hosts, routing in ad hoc networks. Okay, so we will see one by one what are the functions, what are the principles of each routing algorithms. So this diagram shows the conflict between fairness and optimality. Okay, so if we talk about any stable algorithm, it reaches equilibrium and stays there. So there are two parameters, fairness and optimality. As a simple example of this conflict between fairness and optimality, this figure shows, suppose that there is enough traffic between A and A dash. There are some nodes A, B, C, A dash, B dash, and C dash, X and X dash. So suppose there is enough traffic between A and A dash. Here, A and A dash. Between B and B dash, and also between C and C dash. There is enough traffic to saturate the horizontal links. Okay. To maximize the total flow, the X to X dash, if we want to maximize the total flow from where to where, from X to X dash, traffic should be shut off altogether. So unfortunately, X and X dash may not see it that way. Some compromise between global efficiency and fairness to individual connection is needed. Before we can even attempt to find the trade-offs between fairness and optimality, which is shown in this diagram, we must decide what it is we seek to optimize. Minimizing mean packet delay is an obvious candidate, but so is to maximizing total network throughput. So we have to maximize total network throughput. Okay. So these two goals are also in conflict, since operating any queuing system near capacity implies a long queuing delay. So as a compromise, many networks attempt to minimize the number of hops. Hop means node. Hop to hop delivery means node to node delivery. So to maximize total flow, or we can say to maximize, because reducing the number of hops tends to improve the delay, and if we reduce the number of hops, it reduces the amount of bandwidth consumed, which tends to improve the throughput as well. What is our objective? Our objective is to increase the throughput in the network. Now, the optimality principle. We are not going to any specific algorithm, routing algorithm till the time. So before we get into a specific algorithm, it may be helpful to understand that one can make a general statement about optimal routes without regard to network topology or traffic. So this statement is known as the optimality principle. It states that we see in this diagram, if router J in this diagram, there are so many alphabets are written A, B, C, D, and there are so many points. So these points, these dots, acts as a router in this network. So it may be the case that if router J is on the optimal path from router I to router K, we are talking about this router J. Router J is on optimal path from the path I to router K. There can be so many paths. Then the optimal path from J to K also falls along the same route. To see this, we can call the part of the route from I to JR1 and the rest of the route R2. If a route better than R2 existed from J to K, it could be concatenated with R1 to improve the route from I to K. This is contradicting our statement that R1, R2 is optimal. So there can be many cases of optimality. It depends on the situation. Okay. So in this diagram A is showing a subnet. Subnet means a part of network, because we cannot draw whole network on a paper. So this is the part of the network where we have to understand the concept, and the part B is the sync tree for router B. What is sync tree? As a direct consequence of the optimality principle, we can see in this diagram that the set of optimal routes from all sources to a given destination. If destination is K, there can be so many sources from where we have to reach at K. So we can see that the set of optimal routes from all sources to give destination to a given destination form a tree rooted at the destination. Such a tree is called a sync tree. So here sync tree is made for the router B, because B is the destination in any case. Okay. And it is shown in the figure, where the distance metric is the number of hops. Number of hops means the number of the nodes. And it is also important to know that a sync tree is not necessarily unique. Other trees with the same path length may exist. So the goal of all routing algorithms is to discover and use these sync trees for all routers. Okay. So this is the importance of the optimality principle. Now, shortest path algorithm. Here we have used Dijkstra algorithm for the shortest path algorithms. Dijkstra algorithm is a single source shortest path algorithm. In this diagram, there are 5 steps. There are 6 steps. The first 5 steps used in computing the shortest path from A to D means in this network, A is the source and D is the destination. So there can be the possibility of multiple paths, but we are interested to find a path having shortest distance from A to D in this case. So for this we have used Dijkstra algorithm. In Dijkstra algorithm, one by one step is followed, and after that it is found that the actual distance from source to destination. So we call Dijkstra algorithm as a single source shortest path algorithm because there will be a single source and we can find the destination, shortest path to the destination, and except the source all the other nodes can be destination. And after applying the algo or after applying the Dijkstra algorithm, we can find the shortest distance. In this case source is A, so we can answer the questions that what will be the shortest distance from A to B, from A to C, from A to G, A to E, A to F, A to H, and A to D. Okay, so this is the shortest path algorithm, and this is very important. Now flooding. So this is the code of flooding. So first of all, I'm going to tell you what is flooding and how it works. So flooding is another static algorithm. A static algorithm means it takes the decision in advance. It takes the routing decision in advance. So how flooding works? In any network in which every incoming packet is sent out on every outgoing line except the one it arrived on. For example, if in this figure A, if we apply flooding, if packets are transferred from this node A, router A to router B, so in flooding, B transmits all the forwards all the packets from B to C, B to E, because except incoming line, it forwards, it sends the packets to every outgoing line. Okay, so I think you all are getting my points. So flooding obviously generates a large number of duplicate packets. In fact, we can say an infinite number, unless some measures are taken to dampen the process. One such measure is to have a hop counter contained in the header of each packet. I have already told you about the header. Header contains the address of sender and receiver and the time to live field. Time to live means how much time it will survive in the network before reaching to the destination. So there is TTL, time to live. So there should be hop counter contained in the header of the each packet, and which is decremented at each hop. If it reaches at any node, the counter is decreased by 1, with the packet being discarded when the counter reaches 0. This can be a situation or method if the counter is decremented. When this situation will arrive, that if the counter sets to 0, the packet is discarded in the network. Okay. So this is the technique which is used in the flooding. If the sender does not know how long the path is, it can initialize the counter to the worst case. Worst case, what will be the initialization of the counter? The full diameter of the subnet in the worst case. So there are some variation of flooding that is slightly more practical, is selective flooding. What we do in this algorithm, the routers do not send every incoming packet out on every line, but it sends only on those lines that are going approximately in the right direction. So this is the concept of flooding, and these are the implementations of flooding. Okay. Now the distance vector routing. So distance vector routing, if we talk about the modern computer networks, it generally uses dynamic routing algorithms rather than the static, which we have discussed earlier, because static algorithms do not take the current network load into account. So two dynamic algorithms, in particular distance vector routing and another is link state routing, are the most popular dynamic routing algorithms. First of all, what is distance vector routing? Distance vector routing algorithms operate by having each router maintain a table. We can say table or a vector. Okay. So giving the best known distance to each destination and which line to use to get there, these tables are updated by exchanging information with the neighbors. So the distance vector routing algorithm are sometimes called by other names. What are the other names? Bellman-Ford and the Ford-Fulkerson algorithms. Okay. And it was the original ARPANET routing algorithms and was also used in the internet under the name RIP. Okay. So we can say that distance vector routing is the dynamic routing algorithm, and which is very much used, or we can say it is very much popular. Okay. So in the next lecture, I will tell you in the detail about the distance vector routing. Thank you. So each and every routing algorithms has its own advantage and disadvantage in comparison to other. So other routing algorithms we will discuss in the next lectures.